This first lectures today will be delivered by two faculty members, Professor Harish Pillai and Professor Ghorpade. I think he just, oh yeah, he's here. Uh, so Professor Pillai works in control systems or systems theory, and he'll be talking about some aspects of linear algebra and graph theory. And so most of the lectures we are going to have them on Blackboard, but some of us would also use presentation slides. So the Blackboard lectures are all getting recorded and then they will be available to you. But right now, it would be nice if you can take lecture notes because we'll be needing them probably in the afternoon when we do sessions in Scilab. Okay, so thank you. And with this introduction, I'll hand over to Professor Pillai.
I have to unfortunately be the opening batsman, and one needs to test out the pitch initially. Now, from the introductions, I heard there seems to be a sizable number of people from mathematics and quite a few from mechanical engineering. Not very many from electrical, which is where I come from. Yeah. There are a few people, of course. So what I'll try and do is initially talk about some aspects. I would assume that all of you are familiar with basic linear algebra, but I would introduce a few methods of looking at aspects of linear algebra which are quite helpful when one goes into certain specific applications. So, so the object that one studies in linear algebra are linear maps. Yeah, and these linear maps, okay, so we could think of this linear map as some function f going from a vector space V to a vector space W. Both V and W are vector spaces, and there's this vector space structure, which I hope I can assume all of you are familiar with. Yeah? All right. So this F is supposed to be a linear map. Now, what exactly do we mean by a linear map? Well, there is this set of properties that the linear maps would enjoy. So if F takes the vector V1 to, let's say, W1, and it takes the vector V2 to W2, then the linear property tells us that if I take a vector which is, say, alpha times V1 plus beta times V2, then the same F would take you to alpha times F of V1 plus beta times F of V2. And so the vector that you get to is alpha W1 plus beta W2. Now this property of linearity actually makes things quite good in some sense. Because if you have to define a linear map, then one could make use of this property and actually define the complete linear map with very little information. Okay, so for example, let me take this V to be the space R cubed. Yeah, by R cubed I mean a 3-tuple of real numbers. Okay, and let W be another vector space, let's say R squared. By that I mean a tuple of 2 numbers. Okay, and now let's talk about a linear map. And let's say this linear map is something which takes the vector 1, 1, 1 to the vector 2, 3. All right. Now, once we know 1, 1, 1 goes to 2, 3, then we can immediately say that the vector 2, 2, 2 will go to 4, 6. Yeah, and so on. So all the things which are linearly dependent on 1, 1, 1, you can get it by taking multiples of this 2, 3. All right. Now let's also say that f takes the vector 0, 1, 1 to 3, 2. Okay. Once we have specified where this vector goes to and this vector goes to, now any vector which is a linear combination of these two vectors also we can find out. Yeah. What that means is, suppose we are given this vector 2, 5, 5. This vector 2, 5, 5 is really 2 times 1, 1, 1 plus 3 times 0, 1, 1. Okay, and so the vector 2, 5, 5 under this map F would map to 2 times 1, 1, 1 goes to 2, 3, and 3 times 0, 1, 1 goes to 3, 2. So it maps to 10 and 6, 3 2s are 6 and 6, 12. Is this okay? Yeah? Sorry? Is it 13? Sorry. 9 and 4, 13, yeah. All right? And so any vector that you can get by a linear combination of these two vectors, the linear map will take it to a linear combination of these two vectors. All right? Now, in addition, let's say f also takes this vector 0, 0, 1 to 1, 1. Okay? Now, if you take any linear, combination of these three vectors, then the corresponding linear combination of these vectors will give you where it goes to. All right? So, for example, if you have this vector 2, 3, 4, so this 2, 3, 4 is 2 times 1, 1, 1 plus 1 times 0, 1, 1 plus 1 times 0, 0, 1. Okay? Which means 2, 3, 4 would go to 2 times 2, 3 plus 1 times 3, 2 plus 1 times 1, 1. That's 4 and 3, 7 and 8 and 6, 7, 8, 9. That's where it goes to. Okay? And now, this being a three-dimensional space, these three vectors form a basis for this space. And once you specify where the basis goes to, you specified the complete linear map. Is that okay? And so now, if you take any vector in R3, you know precisely where it goes to. Now, amongst the various bases that you can take for R3, there's a standard basis. Yeah, and the standard basis is given by 1, 0, 0, 0, 1, 0, and 0, 0, 1. Yeah, I would use E1, E2, E3 to sort of represent this. Okay? And why we call this the standard basis is because if you have a vector A, B, C, then that vector is A times E1 plus B times E2 plus C times E3. Okay? So, suppose we have been specified this linear map, we can find out where E1 goes to. Yeah, so where does E1 go to? E1 is 1, 0, 0, and this is really 1, 1, 1 minus 0, 1, 1. Okay, and so E1 maps under F to, what does it map to? It's this maps to 2, 3, and this maps to 3, 2. So 2, 3 minus 3, 2. So minus 1, 1. Okay? Where does 0, 1, 1 map, 0, 1, 0 map to? So 0, 1, 0 right? And so it maps to 3, 2 minus 1, 1. So that's 2, 1. Okay? And 0, 1, 1, 0, 0, 1, we know where it maps to 1, 1. Okay, I put these three terms together, minus 1, 1, 2, 1, 1, 1. This is the matrix that represents that linear map. Okay? And so now if this matrix I multiply with 1, 1, 1, I end up getting 2, 3. All right? So importantly, whenever you have a matrix, the first column of the matrix is, the matrix of course defines a linear map, and the first column is precisely where the vector E1 goes to. The second column of the matrix is where the vector E2 goes to. The third column is where vector E3 goes to. Okay? And so what you have to generally think about is whenever you have a matrix and it's multiplied by A, B, C, what you're really doing is minus 1, 1 times A plus 2, 1 times B plus 1, 1 times C. So what you're really doing is take a linear combination of the columns of the matrix. Is this fine? So now that we have a linear map like this, we will represent the linear map by, let's say, some A, and let's say A is given by this matrix minus 1, 1, 2, 1, 1, 1. In general, this could be some Rn, and this could be some Rm, and this would give rise to a matrix A which has m rows and n columns. Okay? Now, given any matrix like that, there are some subspaces that you can associate with that matrix. Okay? And in fact, there are 4 subspaces, and essentially giving us those 4 subspaces is equivalent to giving the linear map. All right? So let's look at what these subspaces are. The first one of them is what I would call the image of A. Okay? So I would denote this with im A. This consists of all, okay, so if I use this abstract V and W, it consists of all W in W such that there exists a V in V is okay. Yeah, is that definition clear enough? Yeah? So image of A consists of vectors here in W. Yeah? So this is the first of the subspaces that I'm talking about. So for this particular example, what is the image of A? Oh yeah, all vectors in R2. Yeah, essentially because if I take this vector 0, 1, 1, 0, this 1, 1, 0 maps to 0, 2. Okay, so half of this will map to 0, 1. All right, and if I take this maps to 1, 0. Okay, and so this is like 0, 1. I mean, okay, so if I take half of this, it maps to 0, 1. Now, any vector in R2 is a linear combination of these two. And so you can reach that vector by taking the appropriate linear combination of these two guys. So everything in R2 is in the image. Okay? So in this particular example, image of A is all of R2. Okay. The next subspace that we are interested in is kernel of A. Yeah. Okay. So I'll define kernel of A in this way. Kernel of A is all those vectors V such that AV is equal to the 0 vector. Okay? So, so for this particular example, what would be kernel of A? 0. Well, yeah, 0 vector, of course. By the way, for linear maps, the property is that 0 vector always maps to 0 vector. So 0 is always there, but is there any other vector which is in the kernel of this? Sorry, what was that? 1? 1, 0? 1. So if you have A acting on 1, 0, 1, it gives you 0 and 2, right? Sorry? 1, 2, minus 3. Okay. If you have 1, 2, minus 3, so yeah, that gives you 0, 0. Okay. So in this particular case, kernel of A, in fact, turns out to be the span of this 1, 2, minus 3. Of course, if you now take linear multiples of 1, 2, minus 3, that will also go to 0. Huh? Let me put it this way. This is okay? Yeah? And I'm sure you have come across something called the rank nullity theorem. It says that the dimension of image of A plus the dimension of kernel of A is equal to the dimension of V. Yeah, in this case, the image of A was R2, so dimension was 2, and kernel of A is this one-dimensional space. This is okay? Yeah? All right, so we have got the second subspace which is associated to the matrix A. Now there are two more subspaces. Okay, the next subspace is, all right, image of A transpose. Yeah. If I transpose this A, of course, it looks like a 3 cross 2 matrix. Yeah, A is a 2 cross 3 matrix. If I transpose it, it looks like a 3 cross 2 matrix. But I won't transpose it. I will keep A as it is. But what I will do is I will multiply A, so minus 1, 1, 2, 1, 1, 1, by row vectors on the left rather than on multiplying on the right. Yeah, and I would be doing effectively the same thing. Is that okay? So if I take a row vector x1, x2, then the result of this would be a 3 vector. So suppose I take x1, x2 to be 1, 2, then I will end up getting, then I'll end up getting 1 and 4 and 3. Right? But note that this, the way we are getting this is 1 times this row, minus 1, 2, 1, plus 2 times 1, 1, 1. This is okay? Yeah? And so if I had taken the transpose, of course the transpose would have been minus 1, 2, 1, 1, 1, 1, and post multiplied it by 1, 2, I'll get the same result. Huh? All right? But we will just think of that as multiplication by row vectors. And so image of A transpose is essentially everything, all 3 vectors that you can get as a linear combination of the rows of A. This is okay? And what do you think is the fourth one? Is going to be the kernel of A transpose. Yeah? Okay. If I think of A as a map from Rn to Rm, then A is a M cross N matrix. So image of A is going to be a subspace of R M, and kernel of A is going to be a subspace of Rn. Image of A transpose is going to be a subspace of Rn, and kernel of A transpose this is okay. By rank nullity theorem, we had dimension of image of A plus dimension of kernel of A is equal to dimension of V. Yeah? We can again use the rank nullity theorem, dimension of image of A transpose plus dimension of kernel of A transpose. This is going to be dimension of W. Okay? In this particular case, dimension of this was 2, dimension of this was 1, and they added up to 3. What about dimension of image of A transpose? How much is the dimension of image of A transpose here? In this particular example? 1? No, it's not 1. It's going to be 2. Yeah, because if you look, this is one vector that you can reach. Yeah, this is another vector you can reach, and these two vectors are linearly independent. Yeah? And all linear combination of these two vectors you can reach. So the dimension of image of A transpose is going to be 2. Dimension of kernel of A transpose is going to be 0 because dimension of W we know is 2. This is okay? Dimension of image of A and dimension of image of A transpose is the same, and they will always be the same. And in fact, we give a special name for it. We call it the rank of A. So rank of A is the same as this is fine. Okay? All right. So I'm sure you have seen most of what I've been talking about in some form or the other before. So let's do something. Let's break out to some example. And the example that I'm going to use comes from graph theory. So, how many of you know what graphs are? Okay. All right. So, in general, graphs are thingies that consists of nodes. Okay. It depends on where you come from. Yeah, which branch you come from. Some people call it nodes. Some people call it vertices. Doesn't matter. Okay. It consists of these guys. So I will, okay, let me use the symbol V for that. Yeah, and there are other objects which I'll denote by E. These are called edges or branches. This depends on where you come from. Yeah, different people use different languages. Okay. So here is an example of a graph. Yeah, these guys are the nodes. So let me call it 1, 2, 3, 4. Yeah, and the other lines which join the nodes are the edges. Okay, so let me name them A, B, C, D, F. Okay? Yeah, is this fine so far? So this, of course, is a general graph. If for these branches you put some arrows, then it would be called a directed graph. Okay, so let's say some arrows is okay. Now, given a graph, one could write out what's again known by various names, adjacency, adjacency matrix, connectivity matrix, incidence matrix, various names are given for this same thing. Yeah. Okay, so let me explain how you construct this matrix. Of course, again, it depends on the background, depending on where people come from, they write out this matrix in different ways. The way I'm going to do it is, I'm going to write a matrix where I have nodes here. Yeah, so the rows correspond to nodes, and the columns would correspond to branches. Okay, so we have 4 nodes, 1, 2, 3, 4. Yeah, and we have 6 branches which we have labeled A, B, C, D, E, F. Okay, and I'm going to fill up this matrix with some information, and that is dependent on this graph. Yeah, and of course what I mean by that is, if you're given this matrix, you can construct the graph and vice versa. Yeah, so what I'm going to do is I'm going to take each branch. So let's take that first branch A. This starts from node 1 and ends in node 4. Yeah, because the direction is this way. So what I'm going to do is, for node 1 branch A, I'm going to put a 1 because it starts from there, and since it ends in 4, I'm going to put a -1 there and zeros. Okay? For branch B, what should I have? 0, 1, 0, -1. Is the construction clear? Branch C, branch D is going to be 1, 0, -1, 0. Branch E is going to be 0, 1, -1, 0. And F is going to be 0, 0, -1, 1. Is this clear? Yeah? So we have this matrix A, which is the adjacency matrix. Yeah? And of course, from whatever we have discussed, there are these 4 things that you can associate, 4 subspaces you can associate: image of A, kernel of A, image of A transpose, kernel of A transpose. Okay? All right, now let's do one thing. Let's think of this graph as a map where 1, 2, 3, and 4 are cities. Yeah, so the nodes are the cities, and the branches are clearly roads. Okay? Now, we could take a vector of size 6, which tells us how many vehicles travel through each one of these roads in 1 hour, let's say. Yeah, so let's say 5, 3, -2, 1, 7, -4. How do we interpret this? There are 5 vehicles which went from 1 to 4. Okay? 3 vehicles which went from 2 to 4. -2 went from 1 to 2, which means 2 went from 2 to 1. This is okay? Yeah, so when you have negative numbers, it just means that it didn't go in the direction of the arrow, it went the other way. Yeah? Okay. Now, what do you think the image of A would be? In this particular situation, what is the image of A? How will you interpret the image of A? Okay, in this particular case, what is going to be the image of A? Under this map, so 5 minus 2, 3, plus 1, 4. Then here I have 3 plus 2, 5, plus 7, 12. Here I have minus, minus, minus. So 5 and 7, 12, but with a minus. Oh, sorry, that was minus already, so that's 4. So, sorry. So this is going to be 8 minus 4, so 4. And this last one is going to be minus 8, minus 4, minus 12. Okay, what does this signify? Second one is 14. Second one is this row acting on this, no? So 3, 2, it's okay? It's fine? Okay, what does that represent? Yeah, of course, that vector is in the image of A, but what does that represent? No. This was the number of vehicles which use these particular roads. And when this matrix acts on that, you get that vector. What does that signify? Of course, let's assume that this was the number of vehicles in 1 hour. What does that signify? Yeah, 4 is the number of vehicles, net vehicles who have accumulated in city 1. This is okay. 12 is the number who have accumulated in city 2. I mean, they came for a ride and they are parked. 4 is the number which have accumulated in city 3, and minus 12, that means 12 guys have left city 4. Is that okay? Yeah? Is there a confusion? Yeah. It looks like the number of vehicles which have parked seem to be larger than the number of vehicles which have left. Yeah, but of course we have not said anything about this network not being connected to the rest of the world. This is okay? Yeah? That's fine? But there could be situations where you can't have something like this. Can you think of any situation where you can't have a vector like this appear? That means accumulation cannot appear? Yeah, so anything which has some sort of conservation. So for example, I could think of this graph as representing an electrical circuit. And I could think of these as currents. But if these were currents, then when I multiply this and I get something like this, that's not allowed, huh? Because current can't just stay there. Huh? Whatever current comes in must leave. Yeah? Current is one example. Another example, this could have been a pipe network which is carrying some fluid. Yeah? So then this much water, let's say water, water flows in there, this much water flows in there, this much water flows in there. That means town 3 is taking all this water. Well, in general, if it's a pipe network, we would assume that whatever water comes should also go. Yeah, of course, we have distributions where you will take off the water and so on, but in general, this is okay? Yeah. So, I mean, one could make use of this in various different ways, and you would have interpretations depending on which application you pick up. Yeah. Yeah. Yeah, so we will do that. We will do that shortly. So, since my background is electrical engineering, I will take this to be an electrical network. Okay? So then, if I call this matrix A, kernel of A, I could think of as all permissible currents. Yeah? Okay. Are you confused about what I have written? Yeah? Okay. So if you're confused about what I've written, here we go. IA, let me assume, is the amount of current that flows in branch A in the direction shown in the graph. IB, similarly, IC, ID, IE, IF. These are the currents in the branches. Okay? Take the first row of the matrix A and multiply it to this. What do I get? I get IA plus IC plus ID, and now I'm saying that kernel of A, therefore this must be equal to 0. Okay? Now, look at node 1. IA, because I am claiming kernel of A are the permissible currents. Yeah? So kernel of A is all those vectors which will map to 0. So the first entry should be 0, right? Yeah? So if I look at that equation IA plus IC plus ID, IA plus IC plus ID, it's the total current coming out of this node. Yeah, but conservation of current, Kirchhoff's current law says that that must be equal to 0. This is okay? Yeah? So that first equation, the first equation that's given is really the Kirchhoff's current law for this node. Yeah, if you look at the second one, what's the second one? Second one tells you IB minus IC plus IE equal to 0. And now if you look at the node 2, that's the Kirchhoff current law for node 2. Is this okay? Yeah? The third equation tells us minus ID minus IE minus IF equal to 0, but that's the Kirchhoff current law for the third node. Yeah, and the last equation tells us minus IA minus IB plus IF equal to 0, but that's the Kirchhoff law for the fourth node. Is that okay? Yeah? So, if you have a vector that satisfies all these conditions, then of course it obeys the Kirchhoff's law in every node. Yeah? Which means that that vector must be something that is a permissible current distribution in this network. This is fine? Okay? So in this particular case, kernel of A are the permissible currents. Okay? All right. Now let's look at image of A transpose. Okay? Image of A transpose, which means this A we are going to multiply by a vector here. And what would be the size of this vector? 4. Yeah? As far as our graph is concerned, there were 4 nodes. Yeah? So for electrical engineers, of course, these 4 nodes, what they can call it, the first one as the potential at node 1, second one as potential at node 2, third one is potential at node 3, fourth one is potential at node 4. Okay? Now if you multiply this, what do you end up getting? In the first entry you will get V1 minus V4. What is that? No, what is V1 minus V4? It is the potential drop across branch A. Okay? The next one is going to be V2 minus V4, that's the potential drop in branch B. This one is V1 minus V2, this one is V1 minus V3, this is V2 minus V3, and the last one is V4 minus V3. This vector that you would get are essentially the potential drops across the 6 branches. This is okay? Yeah? So, image of A transpose. Are the permissible potential drops. Okay? All right. I hope this is clear. What can you say about kernel of A transpose? Kernel of A transpose, that means there must be potentials here such that they map to all zeros. But all zeros means there is no potential drop across any branch. So when can we achieve that? If you take the potentials at every node to be the same. Yeah? So if I take the potential to be all A's, then I should get 0. This is okay? Yeah? So kernel of A transpose, the dimension of this. Okay, kernel of A transpose is going to be the same potentials. Yeah, but that's one dimensional. So dimension of kernel of A transpose is 1. Yeah? Therefore, what's the rank of A? Rank of A will be 3. Yeah. Okay. Dimension of kernel of A plus dimension of image of A is equal to, in this case, number of branches. Dimension of kernel of A transpose plus dimension of image of A transpose is equal to, in this case, number of nodes 4. Dimension of kernel of A transpose is 1, therefore dimension of image of A transpose must be 3, and that must be the rank of A. So this must be 3. Yeah? And dimension of kernel of A is 3. Is this okay? Yeah? Yeah. Yeah, so in electrical terms, if you take these, the image does not make sense. Yeah, so image doesn't make sense, so you're not going to consider that. Yeah. All right, so let me just put some numbers here. Permissible current, dimension 3. Kernel of A, oh sorry, anyway, this is also dimension 3, and this dimension 1. Okay, and I'm not looking at image of A because from the way we are interpreting it, image of A does not make much sense. Yeah, because current can't be accumulating at the nodes. Okay? All right, importantly, the dimension of kernel of A, permissible currents, is 3-dimensional. Okay? It's 3-dimensional, and the vectors, these are vectors of size 6. So not every vector of size 6 is going to obey Kirchhoff's current laws. So these are Kirchhoff's current laws. Yeah? The only permissible vectors are those that will obey Kirchhoff's current laws. And it's a 3-dimensional thing. Okay? Now if you have, in 6-dimensional space, you have a 3-dimensional subspace, how do you represent the 3-dimensional subspace? Yeah, one way is by equations like this. Yeah, so what you have really said is you've given that matrix and you are claiming every vector which is in the kernel of that matrix is going to be something in the subspace. Okay, so I'm interested in subspace of permissible currents. Yeah. So KCL is really kernel of the matrix A. Okay? But suppose you were asked to represent a subspace, how would you do it? Given a space, you have to represent a subspace, how would you do it? Giving equations is one way. Is there any other way to do it? You will give basis vectors. Yeah? Okay? Since the dimension of the subspace is 3, you could give 3 basis vectors, and you could say that every permissible vector of currents is a linear combination of those 3 vectors. Yeah, you could give a basis for the permissible currents. Yeah, now if you give a basis, that would be a, so suppose you give a basis, okay, all right, so let's try and give a basis. All right. Now, what would the basis have to do? The basis has to be vectors of size 6, such that when it acts on this thing, you get 0. Yeah? So let me try and write out a basis. Okay? So, this is a vector, A acting on this vector is all zeros. This is okay? Yeah? Fine? All right. I want to take some other independent vector. So let's say that's a vector which is in the kernel of A. This is okay? I'm coming. Don't let the cat out. This is okay? Yeah? That's another vector. And these two, of course, independent. Yeah? So let me get a third one. So 0, 1, 0. That's another independent vector. This is okay? And so I can claim that every current vector can be obtained as a linear combination of these columns. This is okay? Yeah? And now my question is, what he was trying to break. Yeah? How do you think I've got these? No, not trial and error. A definite way that I've got this. No, I did not solve it. I cheated, of course. I didn't solve it. Okay, this is what I did. You look at this first guy, this first vector. What are the guys involved here? IA, IB, and IC. Right? Look at the graph. What does IA, IB, and IC tell you? It's a loop. Okay? And how are the arrows? That way, and that way. So if I take this to be 1, I'll take this to be -1, I'll take this to be -1 because it's going in the opposite direction. I am just going around this loop. Is this okay? Now it should be clear what that second column is. Yeah, the second column comes from C, D and E. Yeah, so C, D and E, well, that's C, that's D, E, and that's D. Yeah, with the arrows going C, E and D. Okay, so if I think of going this way around this loop, 1, it agrees with this, it disagrees with D, so -1, agrees with E, +1. Is this okay? And the third one? The third one is the loop involving B, E and F. Yeah, so B is that way, E is that way, and F is that way. It's this loop. This is okay? So, kernel representation using that A, image representing using this matrix B. Okay? So, kernel of A, but that's the same thing as Kirchhoff current law, but alternatively it is image of this matrix B. Yeah? What's the rank of this matrix B? Rank of this matrix B is 3. Yeah? So let's start writing out something is here. Dimension of kernel of B is equal to, this should be equal to, it should be equal to 3. Yeah, and dimension of kernel of B transpose plus dimension of image of B transpose should be equal to 6. Yeah, dimension of kernel of B is 0, dimension of image of B is 3. Rank of B is the same as rank of B transpose, so this must be 3 and this must be 3. Okay? What exactly is kernel of B transpose? So you have to multiply with a vector here, right? And the size of that vector is going to be 6. 6 is the number of branches here. Yeah? Earlier we had looked at the 6 vector consisting of all currents in the various branches. So now let's look at a 6 vector consisting of voltage drops across the various branches. What does the first column multiplying the first column tell us? Yeah, it tells us VA minus VB minus VC is equal to 0. That's Kirchhoff's voltage law. Okay, the drop across a loop must be 0. Yeah, when you multiply the second one, it tells you VC minus Vd plus Ve equal to 0. And the third one tells you Vb minus Ve plus Vf equal to 0. And these are the Kirchhoff voltage laws. Okay? Yeah. So there are all kinds of interpretations that one can get. Yeah. And it depends on essentially the kind of modeling that one does. Yeah. Now, as it turns out, the A matrix was not full rank, as in not full row rank. Yeah. But you could make it full row rank. Yeah. If you make it full row rank, one way to do it is just drop one of the rows. Yeah, but that really doesn't get you very far, except once you start doing interpretations. So suppose we look at this particular A, and we decide to drop the last guy. Okay? So if you drop the last guy, so the last guy doesn't exist, that's essentially saying that this fourth guy is the ground. Okay? And then you could think of this as potential at node 1, potential at node 2, potential at node 3. Okay? And now what you have, what do you think this is? These 3 rows, what do you think it does? It gives you the permissible voltage drops that you can have in that circuit. Yeah? The KVL that I wrote down is a kernel representation for it, and this is an image representation for it. Just like currents, we had a kernel representation and an image representation. You had to give 3 basis vectors, so you take linear combination of these 3 vectors, whatever you get, that are the permissible voltage drops in the given circuit. Okay? So one way to do it is as an image representation, the other way to do it is those voltages should obey those 3 rules. That's the KVL. That's the kernel representation. This is okay? Yeah. Of course, what I have shown is just a very small tip of the iceberg kind of thing. Of course, people have then made use of graph theory. You can make use of structures here, like trees and so on, and you can get these equations in a far more efficient manner. Yeah, and the reason why you want it in a far more efficient manner is because when you want to do calculations, this is of course a toy problem, very small circuit. Suppose you had a circuit which had the number of nodes being, let's say, a few thousands, a number of branches being tens of thousands. Then trying to just write out KVL is itself a big task. Yeah, and when you write out, you do not know whether you are repeating things that you have already written out. Some rules that you have written down are rules that have already come by. So you want a organized way in which you know that you do not repeat equations and so on, because ultimately the matrix that you get, the size of that will depend on how you write out the equations. And if you write out too many equations, then you'll be doing unnecessarily huge amount of calculations, which is not required. Okay? So, am I done for time? No, I have time. So, okay, so I will go back to, is this okay, or, yeah, yeah. Yes. Once I have the 3 rows, getting the 4th row is easy. Yeah, because, okay, so this was the graph I had. I don't know how the arrows went. I think it was something like this. No, this was this way. This was up. Okay? A, B, C, D, E, F. 1, 2, 3, 4. Okay, so 1 was between 1, A, this was B, C, D, E, F. Okay, so it was 1, B was, C was 1 minus 1, E was 2, and F was 1 minus 1, 0, 0. Okay? All right, suppose we had dropped this. Yeah, I can get it back very easily. All I have to do is look at each column. This column, 1, so it must be minus 1 here. This one, 1. This one is adds up to 0, so I put 0. This one adds up to 0. This one adds up to 0. This one adds up to minus 1, so I put 1 there. Yeah, the column sums have to be 0. So if I drop any row, it's easy to retrieve that row. No, it's not removing it's you just change the model, that's all. Yeah, instead of writing 4 equations, because if you write the 4 equations, you know that the kernel of A transpose is 1-dimensional. Yeah. If you remove this, kernel of A transpose is going to be 0-dimensional. So you're just removing that possibility by throwing this off. And the way electrical engineers look at that is you assume this is ground. That means you have fixed this to be 0. Now if you fix this to be 0 and you look at the original matrix, what you're saying is V1, V2, V3, and the 4th guy allowed is only 0. Yeah. And because this is only 0, that 4th row is never going to play a role. Yeah. So all potential drops you can get by just this information. This is okay? Yeah. All right. Okay. Now I guess you know that when you're trying to solve these equations in various contexts, you end up getting some equation like AX equal to B. Yeah, and you want to solve that. All right. When is it possible to solve this? Well, A needn't be square. Like the A that we are looking at is a is a fat matrix. I mean, I could have A to be a 3 cross 6 matrix, like the A's that we were having. Yeah? And I want so in that particular case, it was IA, IB, up to IF. Okay, so I don't want IA. Okay, so suppose I have that A, and I want to find a X such that this is equal to some B. How am I going to do that?
In terms of rank, it is A column B rank will be same with the
Rank of A and augmented A, what does that mean?
A column B.
A along with B should be the same. Okay, that is correct, but what does that mean? Yes, it should be possible to write B as a linear combination of the columns of A. Yeah? Which means Ax equal to B is solvable if yeah. All right, so now the question is, how do you check that B is in the image of A? Suppose you just wanted to check B is in the image of A. How will you do that? No, they need not be. I mean, in this case, certainly they are not going to be. Column vectors, there are 6 of them, and each is of size 3. So there's no way that they are going to be linearly independent. Yeah, that's one problem. This could be another problem. A could look like that. Doesn't matter whether it's a problem like this or a problem like that. It's solvable if and only if B is in the image of A. Okay, so now the question is, suppose you are given the matrix A and you're given B, and you don't want to find the solution, you just want to know if it is solvable. Dimension of kernel of A need not be 0. In fact, it's not going to be 0 in this case.
Rank of A should be rank of A.
Yeah, so that's what she said. Yeah, that is right. But you don't want to do that. Okay. You don't want to do that because calculating that, okay, first of all, you need to calculate rank. Is that an easy thing to do? Yes, no? Is calculating rank an easy thing to do? What is your opinion? Let's take the general opinion. Is calculating rank an easy thing to do? You have extra information, insider trading. Do you think calculating the rank is an easy thing to do? Rank of a matrix? No, so as it turns out, rank of a matrix is not an easy thing to calculate. Yeah, and we do all our maths assuming rank, and we talk about dimension, rank, and so on and so forth. That's not a very easy task. Yeah, of course, I'm not talking about a 2 cross 2 matrix or a 3 cross 3 matrix. These are too small But once you, and these you can calculate by hand, which means you can use infinite precision. Yeah. But when you have large cases and you have to depend on a computer to do the solution for you, then you do not have infinite precision anymore. Yeah? And when you do not have infinite precision, it is not an easy task to find a thing like rank. Yeah, and I guess you can appreciate why that is the case.
So, say that you do revert type of thing in the surface that kind of graph.
Huh?
That way,
That way you can generate the equations well. Yeah? Yeah, that way you can generate the equations well. That is true. Yeah, in fact, that is why one uses graph theory to generate the equations rather than try and write out the equations. Because what you do is you generate this matrix, and then for each branch, there is a way the voltage and the current are related. Yeah, so if it's a resistance, then you know that the voltage drop must be the resistance times the current flowing through it. So you have this, each component has its constitutive relation. So you use that and you put that together to get the set of equations. Yeah. Okay, I'll get back to the rank, but about this. You see, what we are bothered about is B should be in the image of A. So image of A is some vector subspace. Yeah? And how has this vector subspace been specified right now? It has been specified by giving the columns of A. That means a basis has been given. Well, not really a basis, but a generating set. Yeah? What's the other way to represent it? Given any subspace, there are two ways to represent it. One as an image and the other as a basis is image. The other way to represent it is as a kernel. Is that okay? Yeah? So, given this A, there could be vectors which when acting on A gives you 0. Yeah? Those vectors give you the kernel representation for the space spanned by image of A. Okay? Yeah? So I am writing it out and you please think about it. This is solvable if for every V transpose, let me call it V transpose, such that V transpose A equal to 0. Yeah? For every V such that V transpose A equal to 0. This is okay? Yeah? Is this fine? Which one? If for every V transpose, comma, V transpose B should be 0. For every V transpose such that V transpose A is 0, V transpose B must be 0. Only then can you solve AX equal to B. So for example, suppose we had a matrix like that, say 1, 1, 2, 3, 1, 3. Oh. Okay. So what are the V's which will, such that V times this is equal to 0? Rank of this matrix is 2. Yeah, maybe I'll make it simpler for me. Yeah. Okay? Yeah, this is the question. Can you solve this? Yeah? Rank of this matrix is 2. So a V which will, V acting on A is 0. Can you find such a V? Well, if I take 1, minus 1, minus 1, that should do. This is okay? Minus 1, minus 1, 1, acting on this is 0, that acting on this is 0. Okay, so that acting on 472 is not 0, so you can't find a solution for this. Is that okay? Yeah? So suppose you take some vector which is, which satisfies this condition. So let's say 1, 1, 0. No. 1, minus 1, 0. So can you solve this? Yeah, you can, because the solution is going to be 1 minus 2. This is okay? Yeah? And if you don't believe me, let's take another one. So 1, 0, 1. Is that solvable? That acting on this is 0. Yeah, so it should be solvable. Okay, so what combination? 1. All right. Yeah, so yeah.
Is this working as a negative is a power?
Yeah. Yeah, exactly. Yeah. So if you want to find out if Ax equal to B is solvable, and you really are not wanting to solve it, then the best way to do it is image of A. You look at the kernel representation for that, which is all those V's. Of course, you don't need to take every V, but you just have to take a basis. And then that matrix acting on B must be 0. Only then is it possible to solve it. Okay? Yeah, and somewhere along the way you would see that there are processes where, okay, so for example, data, when you build up data, you are guessing something. Yeah. So for example, you have a process and there's something happening and you're observing it over time, let's say. Yeah. And okay, so you are observing at time t whatever is the output. So let me call this x. So ti xi is what you're observing. Okay, at time ti, the output is xi, some process. Okay, now it's your belief that this x can be written as a function of time, not just a function of time, in fact as a polynomial in time, let's say. Okay, so polynomial in time, let's say degree 3. So what does that mean? that it is some a plus bt plus ct squared plus okay. Now we don't know what this ABCD is. So the modeling problem is to find ABCD. Okay, but you have observations. So say at time instant t1 you had x1. Okay, so I do the following: 1 t1 t1 squared t1 cubed. A, B, C, D should give me x1. Okay? I do not know what that polynomial is. I'm trying to find, but I have several observations. My second observation is at time t2, so I do this. Third observation, and so on. I have many observations. Okay? And I have a vector here, which is what I have seen at those time instances. Now, is this vector in the span of these? How do I find out? Similar kind of thing, yeah? If I can multiply it by a matrix, V transpose acting on this must be 0. Yeah? Now, if V transpose acting on this is not 0, what does it mean? Well, modeling by using a third degree polynomial is not perfect. Then you got two choices. You can either minimize the error or you can increase the degree. That's your choice. That depends on what you are trying to do. I've been told I can stop. Okay? Is that fine? Yeah, so right away? Okay, fine.
Actually, 11:30 we have another session.
Ah.
So it will go flow there. So another 5 minutes of revision.
Okay, perhaps one small thing I want to say before. Earlier I made the statement about the rank, so let me say a small thing about rank and calculation of rank. Okay. This is the real line. How many numbers? Infinite. Yeah? How many numbers can you represent on the computer? It's not infinite, it is finite. Yeah? Yeah, so it depends on the kind of precision that the computer is using. So if you look at the computer, typically it represents things as 0.2352 multiplied by 10 raised to some, let's say 3 or something. This portion, I think most of you are old enough to have used logarithmic tables and so on. This is mantissa, and this guy is exponent. Yeah, and the way the number is stored in the computer is in terms of a mantissa and an exponent. There are limits to this. Okay? So one could think of an artificial computer which, okay, of course the computer solves in terms of bits, but let's assume it stores in terms of decimal digits. So suppose you have a computer that stores 4 decimal digits for the mantissa, and for the exponent it stores 2 2 digits. Okay, how many numbers can it store? How many numbers do you think it can store? Okay, when I say mantissa and exponent, there'll be one extra thing for the sign. Yeah. Okay, so let's think of the exponent. I said 2 digits. So it can go from 10 raised to plus 99 to 10 raised to minus 99. Okay, that's 199 of them. Yeah, 0, and plus 99, minus 99. So 199 of exponents. And this one, the first digit is non-zero, and the other digits are anything, 10 digits. Yeah? So total, yeah? That's roughly how many numbers you can store in this computer. This is okay? Yeah? And these numbers, mind you, are not distributed equally spaced on the real line. Yeah, how do you think is the distribution? 0, 1, minus 1. Between 0 and 1 and 0 and minus 1, there's a huge portion. In fact, half of these numbers is between minus 1 and 1. All those with negative exponents. Right? Yeah, so this is not even equally distributed. So as you go larger and larger numbers, there are very few numbers that you can represent in this computer. Okay? So now given a number, when you try to represent it in the computer, you do one error, which is the round off. Because you convert it into a number that you can store in the computer. Okay? The second number, when you do that, again you round off, you do something. Then suppose you have to do an operation between these two numbers. When you do the operation between these two numbers, if you do by hand, you get an answer. But that answer may not be representable here. So now again you do one more round off. Is that okay? So when you do a lot of such computations, do you in fact end up getting the real answer, or do you get some answer? Is that okay? So by hand to calculate with small matrices, yes, it looks perfect. You can find out what the rank is and you can do that. But when you try to do it for huge matrices, this may not be an easy task.